Good afternoon, Professor.
Good afternoon, Caroline. Good to
Good afternoon, Professor.
good after. Oh, wait a minute. Now that was Amy. Yes. Good afternoon. Good afternoon. Okay. So good afternoon, Caroline. Good afternoon. I believe that was Amy K. I believe it was Amy K. Good afternoon, Amy C. Okay, I'm going. Okay. Good afternoon, Amanda. Good afternoon. Somehow that was very. Was that it? That sounded very like Renaissance somehow. I don't know. Good afternoon, David K. Good afternoon, Kevin. Lynn. Good afternoon, Amanda. Good afternoon, Kimberly. Someone else is here. Okay, we'll do this quick. Hi. I actually look a little bit more nervous today than usual. So, all right, I better get. Good afternoon, David, and almost happy birthday. Good afternoon, Sophia. Good afternoon, Caitlin K. Good afternoon, Amy C. Good afternoon, Chloe D. Good afternoon, Alicia H. Good afternoon, Adon. You. Oh, okay. Oh, wait, direct chat person. Okay. Huh. Wait, if I didn't hold on, maybe not. I'll check right now. Did I not respond? Wait, okay. Hold on. We're gonna get going. But I usually am pretty good about emails these days. There's a question about hold on. Maybe I didn't. Okay, direct chat person, if you direct chat, there's only one direct chat person, so you know who you are. So I may not have, which is hang on for a second after class, if possible, direct chat person. I'm sure it's fine. I mean, but yeah, no, I usually actually do respond to emails like that. So I don't, so I'm okay. So please just hang out. Okay, thank you. Okay, thank you. Okay, great. Okay, so everyone, I'm looking right now. Yeah, I actually don't see it. Huh. Okay. Everyone, and there's more people coming. Sorry. Wait, okay, we're coming. There's people in the waiting room. And we're going to I don't know which is worse these days, my technology issues or my dog issues. Okay. What I'd like to, more people in the waiting room. Sorry. And of course, Zoom just stopped on my board. Okay, what we're gonna obviously today is about the midterm. And again, if I ever sound at all frantic or something, it's my problem, not yours. It's because I don't want you. I'm not. Oh, good afternoon, Savannah. All right. Like the more authentic you can be on this midterm that you will find in Google Classroom tomorrow night and that you will take home and it will do at your leisure and that you will turn it. Two things to be rigid are turn it in on time before 12:15 next Monday, or if not, communicate with me and make sure I got the communication. And come to class 12:15 next Monday, or if you can't communicate with me, blah, blah, blah. But other than that, please just remember that you're not competing against me. You're not competing against your colleagues either. You're probably just competing against a side of yourself, at least if you're anything like me. The more just honest and you can be about your exam, the more you can honestly try to understand this material and honestly try to convey what you have honestly learned about the material, really, the better shape you'll be in. It's an unusual exam that way, or it's whatever. It may be unusual to some of you what the expectations are, but you don't have to push anybody out of the way to get to achieve in this class, including me. You just have to push your weaker self or whatever self out of the way. Okay, blah, blah. All of which is, but again, if you have any questions, some people have already texted or emailed me with just like questions about like, are you really saying this? Or I'm going to make sure I have this straight, and feel free to do that. But when in doubt, assume the exam is designed to try to help you actually learn enough to actually get a really high grade and actually feel happy about physics. Okay, anyway, whatever. On that note, We're going to continue going over the pre-midterm today. There's one big problem that I think needs to be talked about in the pre-midterm today. We're not going to talk about everything in the pre-midterm today. I think you'll see solutions in Google Classroom to most of it. You have to be a little bit careful looking at them. Like sometimes they're in a different order or, some things like that. And sometimes I will change the numbers on the actual midterm. So, you have to use it as a guide, not as a direct verbatim copying thing. But the thing I really want to make clear is please note that there are 2 YouTubes put in your classroom from Monday, 1 YouTube from your actual class, 1 YouTube from the other class. I don't know if you noticed that or not, but please do take note of that. That's very on purpose because I on purpose did 2 different problems in the 2 different classes so we could see as much as possible. So please note that I went over the Yaver bomber problem in the other class on the theory that you can now watch the YouTube and there's no point in me going, all right, and then same thing with them. And I'll maybe do the same thing again today. So please note that. Last thing, there was something else, but okay. Oh, good afternoon. Good afternoon. Awesome. I'm putting my board back. So putting the board back. Sorry, sir. All right. Well, I'm just going to. Is the board coming back? Yeah, the board's coming back. Okay. If just like yesterday, I think. Well. Okay. Okay. The boat and stream problem we did yesterday, which some people hung back and asked me some questions about at the end of class, very, very wise questions that I tried to answer, of course, but that really show that it's really worth stepping back from that boat and stream problem or the river, the creek paddle problem, whatever. It's a classic problem. I didn't make it up. That problem was made up by a famous Russian-American Nobel Prize winning physicist who made up that problem, honestly, and caused a big stir with that problem to demonstrate to the world, frankly, a fundamental distinction between physics and math. A ton of mathematicians did all this complicated stuff and got it right, but after a really long time, and some of them got it wrong. And the physicists, by and large, did it much faster and easier. And he was trying to show how these concepts of Galileo's principle of relativity really actually help us solve what look like just raw computational problems. Okay, so I highly encourage you. I'm looking in the chat. Sorry. Okay, good morning. Awesome. I highly encourage you to really try to get your mind around Galileo's principle of relativity. There's a reason we make a big deal of it at the beginning with train of thought. For everybody, every single semester, it seems like this just very philosophical thing that doesn't it seems like over here, like it doesn't help you solve problems. And there's all these different forms of it. I encourage you to go back to your notes and see there's form number 1, form number 2, form number 3, form number 5, the more you can see how they're all sound like they're saying different things, but are really ultimately saying one big thing, the more you're getting physics. And if you want to see how those forms help you computationally, yesterday's problem was one big example. The problem I'm about to do in 2 minutes from somewhere else in the practice midterm is another big example. And this right here is I'm reminding you, this is the expanded version of form number 4 of the principle, and it's the most mathematical looking version of the, it's the most mathematical of all the forms. That's my dog. Just to remind you again, if you have any 3 objects, A, B, and C, if you have one object, the velocity of a object to itself is always 0. That's really what we're trying. Whenever we say frame of reference or perspective, when we say get in the perspective of the bottle, as in yesterday's problem, or I'm looking at the problem from the frame of reference of the water, what I'm really saying is I'm in a perspective where the water is going at 0 miles per hour. To be in a perspective or a frame of reference is to view that object as stationary. Every object is stationary relative to itself. That's what subpoint 1 here says. Subpoint 2 says if you have 2 objects, then whatever I'm doing from your perspective is exactly the opposite of whatever you're doing from my perspective. If I'm going 60 miles an hour to the north past you, then you're going 60 miles an hour to the south past me. And then number 3, so notice like the first subpoint is how velocities apply to single objects. And the answer is single objects never have a velocity. Then how they apply to pairs of objects. And the answer is that velocity is always a symmetric relation in any pair of 2 objects. And then subpoint 3 is saying how velocity applies to 3 objects. And that's where things get intense. Once we have 3 objects, they have 3 different frames of reference. Physics is saying that each of the reference frames is equally legitimate, equally correct. And therefore, physics could be done, calculations could be done in any of 3 perspectives if you have 3 objects traveling with 3 distinct constant velocities. However, physics also says this other strange thing. It's a strange thing right around voting day to hear physics is saying you have a choice. You can do physics from this perspective or that perspective, from the frame of reference of one object or from the frame of reference of a different object, as long as they're both going constant velocity. But physics then goes on to say, but you don't have a choice not to make a choice. You have to make a choice. That's actually the thing, honestly, that's going to separate some of your exams from others. It's the people who really sort of get this idea that at the beginning of every problem, you actually have to choose what your perspective is, what your coordinate system is, where is 0, what is 0 attached to, who's moving, who's stationary. Someone in office hours yesterday brought this up to me and said that they were sort of getting the calculations and the computations of this exam, but they were finding it confusing that I kept sort of jumping around from one perspective to another. Absolutely. Like that is what's interesting and confusing about physics, is that we very deliberately, consciously move around from one perspective to another because we believe that the physics can be done correctly in any of a number of different perspectives, but we also believe that the physics has to be done from a specific perspective. We must choose which perspective we're doing it from at any given moment. And some perspectives are a lot more convenient than others. They're all correct, but some are a lot more convenient. And that's where the art of physics really comes in. I will stop babbling in a moment, I promise. I know this all sounds philosophical, but this is all about the thing that a very wise person in office hours said yesterday. He or she spoke for, I think, a lot of people when he or she said, like, I can do the computations, but I have difficulty sometimes starting. I have difficulty knowing which equation to use when, and I have difficulty, like, it seems like we move around from one perspective to another a lot in these problems. She or he was absolutely right to say all that. It's not, she's not, or he's not crazy, but neither am I. This is absolutely the nub of physics and what distinguishes it from raw math. So I'm here to tell you, when I shift in a second and go, yeah, what we have to put our thought into in any given problem is which perspective are we doing the calculations from at any moment. And by perspective, I don't mean where are we standing. I mean, how fast are we going? Are we going with this object's constant velocity and therefore viewing it as at rest, or that object's constant velocity? Like, that's the conscious choice we have to make at the beginning. In fact, from here on, I decree right now, step 1 of every 5-step solution method for every problem, when you do DFP, diagram and fact pattern, from here on in, I'm going to say, if anybody's listening right now, really say, See DFP, choose. Like step one really is diagram and fact pattern where you choose, where you make choices about what your coordinate system is, what perspective you're taking, where is zero, how fast are you going? From here on in, I'm going to say that to every class. I don't know why I never said that before, but step one, when you do your DFP, remind yourself to make choices right then about where your axes are, what frame of reference you're in. Okay, now I'm going to apply that now concrete. So, and that's what we were trying to see. It made such a difference in that boat stream problem. If you choose to be the water, the problem is very straightforward. But if you choose to look at it from the perspective of shore, the problem is very hard. The thing is, if you didn't know that, or you didn't know physics, most people would just look at it from the perspective of the shore because they would innately think that that's somehow like right. But it isn't. Okay, I'm yammering, but I love the questions that I'm getting from all of you in office hours and in email and stuff. They're very like good. Okay, what I'm going to turn to, what I'm going to apply this to, I think, I mean, you stop me, but I think the problem that we all need to see, I'll do a quick screen share here. I mean, I think the other, like yeah, I think the Wile E. Coyote Roadrunner one is a good one, but it's very much like Big Old Duck. And I might do it in the other class today, but the one that I think you really need to see here, I'm just going to switch. Yeah, I think the one that we really need to see is sort of the other thick one. Screen share, hold on. Is it there? Yeah, like this one. Please take out. So part 3, velocity and acceleration in 2 dimensions, free float, which again, if we get cut off today, or if your internet gets cut off or something, I'm telling you right now, this problem is the Toyota and Pontiac problem that we did last week. I mean, it is the same, but it's just more practice of the same thing. But it has to do with applying this concept of frames of reference and perspectives in 2 dimensions. Okay, so can I just get a quick show? Because I'm going to switch my boards again. Actually, well, first of all, can I get a quick show of hands that you know that you see the problem, that you know what problem I'm about to go over? Okay, great. Thank you, Caitlin. Thank you, Caroline. Thank you, Amanda. Thank you, Jamila. Thank you, Kimberly. I know there are other hands. I can't see them right now, but great. Thank you. Okay. Now, can I also put your hands down? I just want to make sure. I mean, or put in the chat or say, I think this is the right problem to go over, but I'm not trying to ram it down your throat. If you've talked outside of class and there's something else you want to see, I mean, I don't want to, is there something else that someone else would rather see than this one? Or does anybody have any smaller questions they'd like me to address? Like, is there any question that anybody wants me to address? Yeah, let me pause for a second. I'm sorry. If you have any question at all about the practice midterm, let me pause for a second for those questions now. If it turns out it's like a very long question, or I'll say that I can't answer it right now, but but it might be short, and so let me pause for a second. Is there anything that anybody wanted me to say anything about in the pre-midterm document, or anything that's unclear, or like a quick exercise there that you wanted a clarification? That's going, were we good? Okay, just making sure. Okay, we're fine. Okay. And am I right? All right, last thing. You saw that there are solutions to pretty much all of it. Raise your hand if you saw that there are if you see the solutions in your Google Classroom. Okay, great. Thank you. Okay, great. Awesome. I'm just making sure. Okay. All right. Then I'm going to switch boards, and I'm going to, well, in fact, okay, before I switch, fine. Now I'm going to solve this problem here, the free float, Toyota and Pontiac in disguise. Okay, in fact, I'm going to leave it on the screen for a moment because some of it I can do vocally. All right, so and by the way, the other reason I'm doing this one right now, I should make this clear. I'm doing this because I think it's important. I think it's big. I think it's the most recent material we did. I think it's harder than some of those. Also, I think this one is not fully solved in the solution. I think this is the one that I didn't put a full solution to so that's the other reason I'm going to talk about it now. But all right, so what's going on here? You've got 3 objects, much like yesterday's problem. You've got a boat, you've got water, and you've got a river bank, or in other words, a shore, right? Just like yesterday. 3 objects. And that's also just like it could be a person on a subway near a subway platform, same idea, or a person on an escalator in a subway station, same idea. Classic situation, 3 different objects going at 3 distinct but constant velocity. Let me also make clear that in this type of problem, nothing is accelerated. Everything is going at a constant velocity. So every different object represents its own possible frame of reference. Each one of these frames of reference is equally correct. Okay, and we're going to look at the relation among these 3 different objects. This is all about GPR form number 4, the 3 different versions of it that I just wrote down on the board a moment ago. Okay. So before I start writing things down, I'm going to do the first couple of of questions or kind of warm up exercises that we can do vocally here. So please take notes or whatever. Okay, so it says, relative to the water, the boat moves at a constant speed of 12 meters per second in a direction of 30 degrees southeast. Okay, there's one of 1,000 different equivalent English ways of saying, it's saying that the boat is moving at 12 meters per second, 30 degrees southeast, relative to the water. Or in other words, in the frame of reference of the water, or in the reference frame of the water, or according to the water, or compared to the water. It doesn't matter what order I put the words in the sentence, but if I were to write, it's saying that if I were the water, I would view myself as stationary and I'd look out and I'd see a boat doing that. Like if I were, right, it's from the water's point of view. By the way, I'm going to keep this up on the screen. What I would do if I were solving this problem right now, if I were setting this up and doing solving it and doing step 1 DFP and making choices, right away, what I would do is I would say something like, let W equal water, let B equal boat, and let R equal riverbank or something like that. Right, I would assign letters to each. So I now know I have 3 different letters standing for 3 different objects. And I'm telling you right now, that sentence that was just given to us in the given, what it in effect just gave us was V, B, W, right? I'm not writing here, but I'm telling you, like, it just gave what, so in effect, V, B, W, velocity of boat relative to water. The order that you write those subscripts matters. The second subscript is always the frame of reference from which you are observing. And the first subscript is always the object being observed. You could say the first subscript is always the target velocity, and the second object is always the reference velocity, if you like, something like that. But so they just gave us VBW. Now, next it gives me VBR. The boat relative to the riverbank gives me constant speed of 10, direction of 45 degrees, something, right? Those are the 2 facts that it gives. So notice it's giving. So this is just like the Pontiac and Toyota, but the kind of facts that it's giving you are slightly different. Please note, if you stand back and look at it, what it just gave you was the same object's velocity, but from 2 different perspectives, right? It's both of those statements are about the boat. Both of those statements are giving you the boat's velocity, but it's giving you the velocity of the boat from 2 different perspectives. 1, how the water sees it, and 2, how the riverbank sees it. And the point is, both those are equally valid. It's literally like saying, from the perspective of Earth is going 0 miles per hour, but from this perspective of the sun, Earth is going 65,000 miles per hour. Both correct, both about the same object, right? Okay, that's the kind of fact that was just given there, just to note. So it gave you VBW and it gave you VBR. Okay, now, A, relative to the boat, in what direction is the water moving? In what direction is the water moving? It's asking, okay, direction. So we need points of compass and an angle. Okay, so this, again, I'm sticking to this screen. I hope it doesn't confuse anybody. The way I'm doing this, what did it give me? It gave me what the boat was doing relative to the water. It gave me VBW, but it's asking here, what is VWB? Do you see what and please stop me if you don't see. That is a subtle but important distinction. Like, order does matter. It gave me VBW, it's asking me VWB. Now, I claim from Galileo's principle of relativity, from the thing that I just wrote down on the board a moment ago, I claim those are always the opposite of each other. Like in general, VAB equals negative VBA. Some of you may be starting to get confused with what's all this A, B, B, W. Like, why does he sometimes use A, B, C, but then here he's using B, W, and R? Like, what I'm trying to tell all of you is when I use A, B, and C, I mean any three objects in general. That's like the memorizer, if you like. Like whatever your three objects are, call them A, B, and C, then they bear certain relations to one another. But now so in effect, I'm saying here, let R stand for A, let B stand for B, let W stand for C. I hope that makes sense. A, B, and C are just general letters. So if I were solving this right now, if I were a student, like doing my solution, I've done step one, in step one, I would have drawn a diagram. By the way, I'm sorry. I'm just talking out here because I'm leaving this up on the screen. In step one, I definitely would have drawn a diagram. Please don't make the mistake of thinking that if there's no diagram in the problem, then you don't have to draw one in your solution. If there's no diagram given in the problem, that's all the more reason that you need to draw a diagram in your solution. People lost a lot of points about that in the Physics 204 exam, to be honest. Like, don't do that. But so step one, I drew a diagram. I wrote down the facts. I made some choices. I said, like, let W stand for water, et cetera, et cetera. Then step two, I wrote my WIQ, like, what's the question? And the question here is VWB equals question mark, right? That's the question. Now, in step three, GDP, general definition and principle, I literally might write down right now, or I should write down for my general definition and principle, for my step three, for part A, I should write down, in general, VAB equals negative VBA, right? That's a general statement that is true of all pairs of objects, whether they're boats or whatever. So now I go to, and that's Galileo's principle of relativity, form number 4. Now I go to step 4, PAW, particular application work. Here in this problem, we have, instead of A and B, we have B and W, we have the boat and water. So here in this problem, to cut to the chase, because I'm talking too long, here, the answer of VWB would be 30 degrees northwest. Because that's the opposite of 30 degrees southeast. If the water sees the boat going to the southeast, then the boat sees the water going to the northwest. I'm just flipping that entire arrow. I'm flipping it on both axes. That's so I wouldn't say negative 12 or something like that. It's asking me for direction. And it's asking me for direction in 2 dimensions. In 2 dimensions, a negative sign is incomplete. It's ambiguous. The negative signs apply to 1 dimension at a time. So if I want to negate both south and an east, I negate them both and I get northwest. So the answer, and you don't have to say 12 or anything, it's just asking for the direction. So to show that you understand the question, the answer here would be VWB equals 30 degrees northwest. Okay, I'm talking way too much. I'm going to go on, but can I just, because I know I'm not writing this down on the board, can I just, again, quickly, sorry, can I get a show of hands if you follow that, if you're good for me to move on? Thank you. Thank you. Awesome. Awesome. That's 4. That's okay. Great. I can't actually see it because I'm looking at the, but great. Thank you. Okay. That's good enough for 6, 5. Thank you. Great. Okay. So I'm going to move on. I really do appreciate how you're paying attention. Okay. So B, now it says relative to the boat. How fast is the riverbank moving? Okay. So it's just extracting little pieces of information, right? And be careful here, like just answer what the question's asking. I will say semester after semester, sometimes people give a lot too much information here. They'll give like the speed at, like in the part A, it's just asking for direction. Just give direction. Some people will give direction and speed. Part B, it's just asking for the speed. Just give the speed. If you give too much, you might think, well, let me just be safe and give a lot of information. The problem with that, sometimes I do take off and then people are upset. Like, well, wait, I mean, I said the right thing. So why are you, but then I just said more. So who cares if I just said more? I gave you the right thing. But the problem is if you say too much, it's not clear that you understand what the question is. If you say too much, then right? Because for that matter, I literally could just write down the whole alphabet and say, look, all the letters are there. I've said the right thing. I just said more than I need. Like, you had to make it clear that you know what the questions are. Anyway, all right. So so for B, the answer, to cut to the chase, the answer is, this is both to it, is 10, period, 10. Because if the sorry, wait, something's in the chat. I didn't mean to. Oh, cool. Okay, thank you. I love this. It's so great. It's like, okay, that's great. That I totally appreciate it. And I'm not laughing. I'm okay, awesome. And then a window just popped up. You know that expression? I think there's an expression like, when the world closes a window, Bill Gates opens 14. No, what is it? When the world closes a door, Bill Gates opens like 15 windows or something. I'm getting all these pop-ups while I'm trying to talk. Okay. So yeah, okay. So just say 12. So the answer is 10. How fast? 10. Because again, VBR equals negative VRB. But you see, the negative doesn't modify the 10. I guess that's what I'm getting at. How fast is the riverbank going? The answer is, how fast is it going? It's just asking speed. The answer is 10. Is it going in an opposite direction? Yes. But so what that would mean is, if I asked, it would be like 45 degrees southeast rather than 45 degrees northwest. But that's how you take care of direction in So I guess what I'm really trying to say, and then I'm going to move on. The answer to B, okay, is 10 meters per second. It's not negative 10, because it just asked how fast. Okay, maybe it's a little bit obnoxious, but please take note of that. Okay. Then C, from the water's frame of reference, at what velocity is the water moving? Okay, you might think this is someone in office hours yesterday, I was really proud of him or her. He or she had an instinct to this, but they didn't trust their instinct because it seemed like a little too easy or something, but no, their instinct was right, and y'all should trust your instincts as you develop them in physics. If you think the answer to this C is 0, you are correct. The answer is 0. From the water's frame of reference, the water is moving 0. VWW equals 0. And that's like an important thing. That's not like, it's not a trick. And what we're really trying to get at, the thing we really want you to believe is, and oh, by the way, the water's reference is just as correct as any other frame of reference, right? This ties back to yesterday's problem. Again, those of you who ever play video games, I mean, no joke, if you play video games and you get used to this idea, or if you drive a car, like in life, once you get used to this, or you ever see certain kind of movies, like once you get used to this idea that from your perspective, you don't move through the world moves past you, like, and they incorporate that in first-person video games and stuff. Like, what we're trying to say in physics is that's not an illusion. That's a perspective. And it's not a wrong perspective, because if it were, then no one would ever believe the earth was moving through past the sun. You know what I'm saying? Like, right? Everybody always views themselves as stationary and views the world as going past them. And we're saying 3 things. 1, you're not crazy when you have that sense. 2, it's correct. 3, lots of powerful physics can be done once you accept that. Like, okay, that's like what this whole test is about in a weird way. And okay, anyway, now D. Okay, now we start talking. Okay, now comes some calculations. I'm going to switch screens in a second. If this is driving some of you crazy, it probably is. Because now we're talking part D from the perspective of the water. At what velocity is the riverbank moving? Okay, whoa. Okay. So this is heavy. We're going to do some math here. And let's back up and realize, like, it's asking if you were, it's kind of like yesterday's thing or Monday's thing. If you were a little water molecule watching the shore go past you, at what speed and in what direction would you see the shore moving past you? Now, if that may be hard for you to picture in a way, but I will say that if it's easier for you, if you prefer to stand on the bank and watch the water go by, that's fine. It might not be as productive a perspective as you think, and it's definitely not as correct a perspective as you might think, but it's fine. Note that what we're asking here is just the opposite of whatever if you stood on the river bank and watched the water go by, whatever that speed and direction is, we're looking for the opposite of that, okay? But either way, It's not given in the problem. What was given is what the boat is doing relative to the water and what the boat is doing relative to the shore. We want to know what the water is doing relative to the shore. Okay. So we're going to have to combine vectors. Oh my God, I'm about to lose my board again. So now we got to do some math, draw some diagrams and stuff like that. We got 40 minutes. I'm going to switch my, to the board here. So pardon me. And of course, I'm about to lose the board again. I don't know why. Okay. And bear with me because, okay. Okay, so first we're going to find, okay, it asks us to find the answer graphically by drawing vector arrows, but let's, so this is, sorry. Okay, I'm assuming that I've already done A, B, and C. I'm assuming that I've already done diagrams and stuff like that, sort of trying to cut to the chase here. But we're asking what's the velocity of the river bank relative to the water. That's what we're asking. Now, the first thing I would do before I even draw the arrows, I want to get some things straight here. I want to get the relations. Like, I want to know, like, are we really being asked to add vectors or to subtract vectors here? In other words, one thing I could say is, okay. I just wrote that, like, yeah, okay. I just wrote down one possible GDP for this, one possible. There are, what did I just do? I just decided, okay, I'm asked for RW, for VRW. So I just took the other two letters and arranged them in the appropriate order for addition. There are a lot of other combinations that would work, and some of them might make more sense to you. You can do any combination that's right, but notice you have to follow the pattern, right? Like AB plus BC equals AC. Velocity of me relative to escalator plus escalator relative to station yields velocity of me relative to station. It always has to follow that pattern or that arrangement, right? So I'm looking for RW. So one way that I could arrange R and B and W to make RW is RB plus BW equals RW. You see what I mean? That's not, I could write other arrangements, but that one's the first one that comes to my mind that solves for what I'm trying to solve for and arranges and arranges the things that I have. But let's also note, like, if I'm trying to solve for what I'm solving for from things that were given, let's also note, like VBW was given, right? So that's convenient. But the other thing, VRB was not given. VBR was given, but VRB, we conveniently were asked for in part A or B or something. right? So in other words, I'm now going to try to arrange the vectors that I have to make the vector that I want. And actually, I'm going to just be very careful about, one of the ones I'm going to arrange is the one that was literally given, and one was one that I found. I'm just saying the order does matter, I guess is what I'm saying. You got to be really careful about tracking these subscripts. And it all comes back to GPR form number 4. But okay, so I now know I've got 2 vectors that can be added together to make a third vector. So I'm going to take 2 vectors and place them tip to tail to make a diagram that shows what the situation is. Like I'm about to do D3, the diagram. Right, so I'm gonna make a diagram that shows what's going on to find the answer graphically, more or less to scale. It's going to be now I would try to put some effort and care into this in your final copy of your exam. I'll try to do that now. So I'm supposed to be adding VRB and VBW. Okay, VRB. So VRB, sorry, I'm going back and forth between screens. VRB, that means sorry. Oh yeah, okay. Okay. So VRB is going to be 10 at 45 degrees southeast. Okay. Actually, that's a little. Right, VRB is 10 meters per second at 45 degrees southeast, because that's what we found in part B. And then it's being added, it's supposed to be added to VBW, I believe, to VBW, which is given in the problem as 12 at 30 degrees southeast. So right, so what I am, and notice, like, I mean, I would hope that in your exam, yours is a little bit more careful than mine, maybe, but so here's my diagram to represent what's going on. This diagram is not going to solve the problem for me. It's showing me what's going on. What that red arrow that I just drew represents VRW. It's a very long arrow, and it's pretty clearly going somehow to the southeast. So when I get so that's trying to say that from the water's perspective, the shore, the river bank, is going pretty darn fast to the southeast. Because in effect, what we're saying is we've got boat going. Yeah, we've got boat going past the water pretty fast into the southeast, but then we've got water going past the boat pretty fast to the southeast. So in the end of the day, the shore is going past the water really fast to the southeast, all of which is to say that the water is going past the shore to the northwest. I'm just looking into any. Okay, I mean, it is a lot to keep track of, but what I should, in the end of the day, get an answer for VRW. That's a big number, like bigger than 10, bigger than 12, but not bigger than 22. I don't know if you can see that in my triangle, but like my final answer should be bigger than 10, bigger than 12, but not bigger than 22, not even as big as 22, right? Because the two vectors are not actually parallel with each other. And it should be pointing somehow to the southeast, probably less than 45 degrees, but maybe even less than 30. Anyway, okay, so now that is the picture of what's going on. That's D3. Now D4, we're going to get an exact answer, and this is where the most work of the problem comes in, the hardest part of the whole problem, and we still have a half hour, so we'll be fine. So in D4, we are solving for VRW. So how do we do this? Okay, what we do, I'm switching screens again. What we do is we're going to take, now what we're going to do here is exactly what we would do if these vectors were displacement vectors. I mean, and this is the physics part too. Like, what's really hard is that I'm talking about all these velocities, and it's hard to keep track of what that means and all that. But now that I've drawn this picture with each one of these arrows represents how fast something's going and in what direction at a given moment, at a given point in space and time. But how they relate to each other mathematically is just as though they were displacements. Like if you look at that triangle, in effect, what I'm trying to find out is how far and in what direction would you walk if you started at the tail of the 10 and you ended at the tip of the 12. I'm just trying to add those two blue vectors together to get a red vector, right? So the way I'm going to do it computationally is zoom in on each vector individually and resolve it into its individual horizontal and vertical X and Y components, right? I'm in effect now, I'm going to do GPR form number 5. I'm going to say that every two-dimensional problem is really two one-dimensional problems occurring simultaneously yet independently. Okay, so what does that mean? It means this. Zoom in on each vector individually. And we're going to pause for a second and move my station. Okay, hold on. Bear with me for a second. I'm just moving, and we'll zoom in on the vectors. That's why they call it a zoom. Okay, hold on. Sorry. Okay, sorry. Okay. I'm just doing this to give you a chance at home to zoom in on your own vector, your own way. Okay, so I'm going to zoom in. No, I should do this more slowly, but right. So we have this VRB equals 10, right? 10 meters per second going to the southeast. So I say that any vector going to the southeast is really independently but simultaneously a vector going south and a vector going east. It's literally the addition of east plus south. And I always first. So I always draw the horizontal one first. That's a trick. That's a tip. That's a strategy for anybody who's been listening. Always draw the horizontal first, and it's literally a vector. It's going to the east, so it has a tail and a tip. And then from the tip of the vector going east, I start the tail of a vector going south. So I make east tip to tail plus south. So east plus south makes southeast. Granted, south plus east also makes southeast. Addition is commutative, but it's always strategically better to start from the horizontal. So, okay, so those are the two legs. So now I say this leg up here is VRBX, so to speak, and this is VRBY, so to speak. And what are they? Well, this one is 10 cosine 45, and this one is 10 sine 45. Only let's also, I should have done this right from the get-go. Like I'm going to say anything north is positive, anything south is negative, anything east is positive, anything west is negative. North, south, east. That's a choice I just made, but now I'm going to follow it consistently. Okay. So cosine of 45 is like 0.707. If you do it on a calculator, right? It's like radical 2 over 2 is like 0.707. So times 10 is approximately 7.07. And this one is approximately 7.07. Okay, so that's that triangle resolved. So I'm just going to put that in one side of my brain, my mind, and then I do it to the other vector. So the other vector was 12. And you might want to use like a straight edge and a compass and stuff. That's, I'm going to try one more time. Sorry. I can't do it. All right. And that's 30 degrees. And that's 12. And so I resolve it again. So this is VBWX equals 12 cosine 30. And this one VBWY equals 12 sine 30. Now cosine of 30 is about 0.866, I believe. So 0.866 times 12. Someone's going to tell me in a second, but I do. Oh, yeah. Okay, so this is about 10.4, and sine of 30 is 1/2. So this is about 6, like 0.00. Okay, so now I have all my facts. Now what do I do with all these facts? Well, the whole idea is that I'm adding these vectors together. The way to add them together is to add their individual components independently, but simultaneously. In other words, I'm going to make, actually, I'm going to do it on the next page. So I'm going to make an XY chart. I'm going to say there's two worlds, the world of this axis and the world of that axis, occurring independently yet simultaneously. And this is VRB and this is VBW, and we're adding them together, right? So VRBX was 7.07. VRBY was negative 7.07, right? Negative, right? Negative because it went to the south. And then same thing with the other. We've got like 10.4, I believe it was, and negative 6.00. Let me just check if that's, yes, right? So I'm tallying, in other words, this is addition, but addition of numbers along each number line individually. That's why our first homework assignment was called number line. Okay, so I add these up. So now I have like 17.5. I mean, I'm rounding significant digits. And then this one, I'm adding up. I'm adding. So -7 plus -6 is like -13.1, doing significant digits, right? So what do I do with that? Now I say, okay. So that means at the end of the day, or like at the end of this addition process, the river, oh, and this is river relative, I mean, this is river bank relative to water. The river is going 17.5 meters per second relative to the water to the east, while independently, but at the same time, it goes 13.1 meters per second to the south, right? These are not distances. This is not how far anything traveled. This is at any given moment, how fast it's going at that moment in particular directions. So at the end of the day, so to speak, we could say, all right, 17.5 to the east. So I drew a vector to the east, and then from its tip, I draw the tail of the other vector going a little bit shorter, like a little bit shorter, 13.1 to the south. So this is VRWX approximately equals 17.5 meters per second to the east. And this is VRY going like 13.1 meters per second to the south. So then at the end of the day, in fact, this hypotenuse that I'm looking for is this hypotenuse, this really long thing that's going to the southeast. This is that red vector from my original picture, right? If I've done it, and the more careful you are on your exam with straight edges or compasses or even maybe rulers to check, if you're drawing things roughly to scale, you'll see, if you really are drawing things to scale, just to be clear, if you're really being careful about then this red line right here, this hypotenuse, is literally going to be as long as the original red line in that original picture, and it's going to be going at the same angle of everything. Like that red line is this red line, only this is how you get it. And honestly, so what is this? VRW equals the square root of 17.5 squared plus 13.1 squared. Which is approximately 21.8. Oh, and remember we said it's going to be greater than 12 and greater than 10, but not greater than 22. And it's very close to 22 because the two angles were so close, right? I mean, if the two lines had been exactly parallel and gone off in exactly the same direction, they would have literally just added as though on a number line, but they were slightly at a different angle. So it's right. This is a very, very like stretched triangle. But okay, 21.8 meters per second, that's VRW. And then this angle is what we want. This angle is going to be the direction of our answer. And I know that I've drawn things nicely here. The reason I always draw horizontal first and then vertical from that is that you notice that my angle is between the two tails of the vectors. It's an angle between two tails, not between a tip and a tail, and not between two tips. It's between two tails. And also, it's an angle that's being measured from the horizontal. That means that I've done something right, honestly. It's between two tails is the angle that I want, like the angle that I'm actually going. But since it's from a horizontal, that means that the answer that I'm going to get is some amount south of east, as opposed to some amount east of south or something like that. Okay, so somehow I've drawn something right, that the angle that's asking to be solved for is an angle that makes sense, I think, physically, intuitively. So what is that angle? It's the arc tangent, right? I mean, tangent of that angle would equal opposite over adjacent, would equal 13.1 over 17.5. So the angle itself is the arc tangent, the inverse tangent, the opposite tangent, tangent to the -1, whatever you want to say, of 13.1 over 17.5, which I cannot do in my head. Oh, and I just looked, for heaven's sake. Okay. So, and you can check, please do check my computation if you can or want in a moment. But I think it's, hold on. Okay. Yeah, so I want the right. So I think it's 36 point. So I think, so just putting the, so I think the answer is V RW equals 21.8 meters per second at an angle of 36.8 degrees southeast. Like this would be my final answer circled. It's a little bit illegible, but my final answer circled to the, and again, this is the thickest, biggest part of the whole problem. I think it involved the most computation. Step 4, PAW, practical application work, is super long here, not coincidentally. But I think my final answer, remember the original question is how fast and in what direction, what's the velocity of the river bank going relative to the water? I think the answer is that the riverbank is traveling at approximately 21.8 meters per second. The riverbank is traveling past the water at 21.8 meters per second, approximately, in a direction of 36.8 degrees southeast. That's the answer. It's approximate just because there's like square roots and arctangents and stuff involved, like not because we're making things up. But it is approximate because we did chop off digits, which also means if you on your exam got something like 22.3 or 21.3, like something around it would be fine. I know we're chopping off digits. We're going to get slightly different answers. That's totally fine. And that's why I'm writing approximate. But definitely your answer should be to the southeast. It should be an angle around, an acute angle around 37 degrees. This is the answer. What does it mean in English? It means if you stood in the shore and watched the river flowing, you would see it flowing to the northwest at like 21.8 meters per second. That's the answer. I think it's like one of the hardest problems in the test. There's a lot of computation there, and there's a couple more questions in this problem, I know, and we've got 13 minutes. I'm going to do those, but is there any can you read my handwriting? I mean, is there any, let me change it. Again, if you okay, I'm going to ask, raise your hand if you basically think you followed that. Oh, cool. Oh, that was fast. Okay, good. No, I appreciate it. That's good. That's great. No, that's good. Thank you. And look, and honestly, and you're not committing yourself when those people, here's the funny thing about physics. If you didn't think you followed that, then please try to practice it. But if you did think you followed that, then please try to practice it. But you get what I'm saying. But good. If you followed it, you should practice it either way. Anyway. And again, if you want to practice, if you're like, wait, I want a problem with different numbers to see then go back to the Pontiac Toyota problem in the homework packet for one thing. But also you could just change these numbers and give it to a friend. You could just change the numbers and it'll still, it'll work. You know what I'm saying? Okay. That's that. Now let me just go on. We've got 12 minutes. Let me go on to the rest of the problem. I think that's the thickest, that's sort of the point of it, but then there's a little bit more. Okay, so then it says create 3 bird's eye view vector diagrams, one from the boat's frame of reference, one from the water's, one from the, okay. This is to show what's going on, right? And it sort of explains here. This is one of those things that if you don't know what it means, then you don't know what it means. But once you know what it means, it's not that bad. This is not a computation. This is a depiction. So we're gonna, okay. So look, we're gonna draw 3 little bird's eye view vector diagrams. Okay, one from the boat's frame of reference. So here, boat. It just wants from the boat's frame of reference, what are the 2 other objects doing? Drawn with vectors. Okay. So here, okay, so like from the boat's perspective, what's the water doing? Well, the water, here, I'm going to switch. No, I'm not. Okay. So from the boat's perspective, we want, in other words, VWB and we want VRB. We want the two other objects, but from the boat's perspective. So VWB is to the northwest. VWB is 12 degrees, 30 degrees. Right. And VRB is southeast. VRB, right, is southeast. Okay, this is diagram 1. And notice these two vectors, right? This is VW, oh, sorry, and VRB. No, I'm doing the boat's perspective, so both these vectors end in B for boat. It's the water according to the boat, and it's the river according to the boat. And notice, and they're each measured, you know, at an angle relative to an imaginary, you know, sort of eastern axis. That's the boat. Then I'm going to do, now I'll do the, and I got my information either from the givens or from anything that I figured out. Then I do from the water. So I'm going to do VBW and VRW, like the two vectors from the water's perspective. So RW, oh, RW is what we just figured out, right? Yeah, so RW is to the southeast and it's long, so RW. And again, honestly, I would recommend that your diagrams be a little bit more to scale than mine. I'm doing this a little bit quickly and a little bit sloppily. And again, too, with your exam, since you've never done it before, the more you prepare and practice, the more you'll notice, oh, wait, we have all the answers to this. You'll notice you have all the answers. So where are you putting your efforts into trying to make yours as presentable and clear and easy to grade and fun to grade as possible? Like, this is more like an essay than, or a project, if you like, than like a typical quiz or test. Like, really try to present, honestly, a little bit better than I do here. Like, I'm a little bit, you don't have a timing factor. So put your effort into making a document that's really a presentation. I mean, not a presentation, but you know what I'm saying? Like, it wouldn't be a waste of your time to really try to put pride into your document, especially, okay, you get my point. But so here's this one. And then the other vector is supposed to be VBW, which is also VBW, which is northwest, VB. Uh-oh, did I do something? Okay, yeah, oh, southeast, okay. So the other one is a little hard to draw, but so it's like, right, do you see what I'm doing? Notice that, and I'm going to do one more diagram, and then we're done with class for today. And then, you know, Godspeed, electron speed, everyone. Again, the test will be posted tomorrow night or by tomorrow night. You could text me or email me before then. Once the test is going, you could please do, once the test is on, by the way, you can text or email if you think there's something ambiguous or possibly even erroneous in the document. If there's something unclear or wrong in the test, definitely bring it to my attention. But I can't help anybody with it once it's started. You can help each other, but I can't really help anybody because then that gets into unfairness, like, because then just so, but anyway, notice, I'm going to draw one more diagram and then we're done. But notice that in each of these bird's eye views, I'm drawing the vectors now tail to tail, not a coincidence. I'm not contradicting myself. In these bird's eye views where I'm in one frame reference at a time, I'm drawing the vectors tail to tail because I'm not adding the vectors now. They're not tip to tail, because if you're really understanding Galileo's principle form number four, you add velocities that are in different frames of reference, like me to the stair to the escalator plus escalator to the platform gives you me to the platform. But me to the escalator and you to the escalator, those don't get added. Those would get subtracted. So these are all, you might want to think about that, but these are all what we mean by, these are all in one frame of reference at a time. And so then the final one, the river bank. So I have to do the two. So I've got the boat going at right, and that's to the riverbank, and then water to riverbank is the opposite of what we just found in the other. So also northwest. So this is hard to draw. So like, I should move this all over. Sorry. No, we're done. So like that. And water is like that. So this would be, we have 3 more minutes. So these are the 3 pictures of what the 2 velocity vectors from each perspective is doing. That's what it's looking for in part E. And then finally, F, we can do this first. F, a leaf is floating on the water, it moves exactly at the velocity of the water. A frog is sitting on a rock in the river, it moves exactly at the velocity of the riverbank. How fast is the leaf moving relative to the boat? So how fast is the water moving relative? It's almost like that's almost a trick question. It's not meant to be, but it's just asking, what's the water doing relative to the boat? Well, the answer is 12. The water relative to the boat is 12. I'm not exactly sure what the point of that question is, but that's the answer. And then it says at a certain moment, this is the point of the question. The leaf is right next to the frog. After 4 seconds, how far? A word got cut off. The word that's cut off should say direction. But after 4 seconds, how far is the leaf from the frog? And in what direction? We've got 2 minutes. So really what we're asking here is, we're asking about velocity of water relative to because the frog is sitting on a rock. Yeah, the frog is doing exactly what the riverbank is doing. So we're asking, what's the water doing relative to the riverbank? So the velocity of the water relative to the riverbank is everything that we just figured out, right? The water, right, is 21.8 meters per second at 31 whatever 8 degrees northwest. So 4 seconds later, it would be 22, approximately 88, I'm rounding, but 88 meters at 31.8 degrees northwest. And that's the final answer to the whole thing. So again, I think you now have a lot of solutions. If I might do a different problem, I'm not sure I'm going to do another class yet, but hopefully you have a lot of solutions. Hopefully you're pretty set to go. I'm switching back screens here again. Text or email me if you have any concerns, but again, just be as honest and thorough and take your time and treat it like a project, not like an exam. Treat it like you're trying to show what you've learned. You're not trying to prove whatever. You get my point, hopefully, but you'll all be fine. It's a pleasure seeing you. I'm done if you're done, but I'll hang out for any quick questions or anything, but have a great day, everybody.
Have a good day, Professor.
Have a good day, Professor.
Bye, Professor. Thank you.
Thank you.
Have a great day, Professor.
Thank you. You too. Thank you. Thank you. Oh, okay. Yeah, hold on. I'll put it in there. Oh, and then someone was, and hang out. I was Alicia. Okay. Yeah. Okay. For everyone, I'm gonna put my contact number. The best way to reach me, and hang on, direct type person. Yeah. Just if you text me, it's fastest to, you can use my regular email. My regular email is in the syllabus and the regular d@J. But the best thing is if you text me at this number, just say who you are, the first time, and then, but yeah, you could text me at that number. And then, okay, and if you don't mind, okay. Cool. Alicia, you're still there, right? Yeah, so Alicia, I'm not trying to be, but just to save. So Alicia, for some reason, I don't see your email, but I totally hear. Just hang on 1 second. Or I mean, Alicia, if you don't mind, just hang on for 1 second. But anybody, or does anybody else have a, here we go. Does any of the rest of you have, and I'm turning off the recording.